welcome to the final. God damn. Welcome to the final workshop of season 4. Chris Lai is not here right now. He's up in Boston winning paper competitions. So I'm gonna fill in for him. My name is Zachary Johnson. I'm a senior here, graduating this semester, going to work for L3 Harris in software engineering. So you're gonna get a little bit of a different perspective here, other than Chris's EE side, where I'm a little bit more software focused. So we're gonna dig into some of the key aspects of what we're gonna do here. We're gonna be primarily focusing on autonomous control. Last season, you might have remembered that before we get started, actually, who here attended the soldering workshop this semester? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Is that 8? Okay. 8 soldering workshop. Keep track of that, please. Who here attended the Arduino workshop last semester? 1. Oh, 2. Okay, we got some newcomers here. Okay. So let me just recap real quick what we did in Arduino last semester. That means we get to go through the nitty-gritty. It was a race where we built Arduino cars that looked a little bit different than this. It was just like an RC car. You had a controller, you would program the controller, you would program the car, and then you would drive it around. That's us, by the way, don't worry about it. We raced around a track, and whoever got the fastest lap, or whoever won a race, it was like a battle royale style. We just lined up about 20 cars and they all went. Whoever won some prizes. We don't have any prizes to offer you this time, but we got trophies. And the challenge this time is not about the controls. It is about autonomous programming, specifically in line follow. But let's go ahead, get into the background. What is an Arduino? Has anyone used Arduino here? Couple you? What are we looking at? What kind of applications are we using with Arduinos? Robotics, just IoT? Prototyping, right? Yep, that's a good one. Anyone else? Are we more approaching Arduino from the side of like programming, or are we just using them just to fulfill like a programmable role, pretty much? Oh, let me turn this down. Let me do this. All right, we'll go ahead and just jump into what is Arduino right now. Ooh, no, we won't. What is Arduino? So Arduino is an open source hardware and robotics prototyping platform. It gets a little bit more nitty-gritty than this. We could say that Arduino is actually the software ecosystem that encompasses a series of microcontrollers. Constructing digital electronic systems, devices, and inventions is what it's for. It's for IoT, it's for robotics, it's for anything where you don't need a desktop computer, a laptop, but you need some sort of way to process math, sensor inputs, or do any other sort of EECE side, but without all the headache. We could use it for simple computing. We can interact with math libraries in order to do trig, basic fast math, other things like that. We already went through the sensors, that it can use sensors. That is its primary use, in my opinion. It's what I use it for. But we can also control motors, steppers, and robotic equipment. This is done through daughter boards where you would use a motor controller. We can get more into that later. But let's talk about the actual microcontroller. Who here is like a CE, computer engineering? All right, how far are you guys into your diploma? You guys learning about like ISR or something like that? Oh, okay. What does that put you then? Like, you have to be past electrical networks, right?
Just learning flipping off.
Oh, okay. All right, so that's fine then. I could lecture to you badly about microcontrollers. So Arduino is not the name of the microcontroller. The Arduino is the chassis and the software shell that encompasses interacting with the microcontroller. The two most common Arduino microcontrollers, or Arduino compatible microcontrollers, are the Atmega 328P. That is the Arduino Uno. That is your most common, your most proliferated Arduino platform. Is the DIP chip. I'm not an EE, I can't go into that more. It is pretty old. In fact, we're looking at almost 2-3 decades going on, engineering wise. And it's really good for DIY because it's cheap. You can just buy a ton of them. And they're everywhere, really. And then we have the second, more, I guess, beefy chip is the Atmega 32U4. It's a surface mount component instead, and it is based on newer technology. Comes with USB 2.0 control. It operates at a faster clock speed. So if you need something that isn't super, if you need an application that requires more computational power, if you're doing a lot of floating point math, for instance, and you need that done more quickly, the 32U4 is probably for you. Otherwise, if it doesn't really matter, just use the 328P. Going on to the actual, the Arduino, I guess, ecosystem, there's different classifications, different names for different sizes. You have the Arduino Nano, Uno, Mega. There are actually a ton of boards. In fact, if just go to this Wikipedia link, see what's up. There is a whole lot of different boards that you could choose from, and it can get kind of intimidating or kind of annoying, actually, to spec the correct board for your application. But what I hope to convey in this workshop is that it doesn't need to be that complicated. Most Arduino boards will get the job done. Oops. What you need to do to decide on that long list of board, what you need is you need to specify what kind of size you need, what kind of processing speed you desire. I just talked about, if you're doing a lot of floating point math, if you're doing a lot of things that require instantaneous response times, you either want more processing speed, processing power. I guess it's sort of, these are sort of connected. We can get into like threads and stuff like that, but not needed. Plus it's utility. And so this utility is talking more about these pins that you have. Larger boards with different chips are going to allow you to connect more sensors, connect more motors, do a lot more with the USB ports, have a lot more like feedback in the LEDs. You even get different print screens. There's some Arduino Unos that is just an anime girl print screen. I have a couple of those for unrelated reasons. But also, there are application-specific reasons why you might get an Uno, why you might get a Mega, why you might get a Nano. Robotics, I can speak for this especially. At minimum, I'm using a 32U4 because I am doing a lot of floating point math. I have a lot of reasons to need to send square waves down certain pins, stuff like that. Fast computations, there are actually faster Arduino boards than the 32U4. There's stuff, I can't remember, it's anything with if you look on like a store listing, you see like ARM Cortex, that's probably like way faster than what you can get with an Arduino Uno Nano. I'm thinking right now. I think we just skip these two. But yeah, we can skip these last two. It's not specific. It's not specifically catered to what we're going to be doing in the lab portion. But also, you can pay attention to if you're an EE like Chris, you really get off on this kind of thing. You can look at the voltage regulator specs. You can see how much abuse these boards can actually take. Because, as we might figure out, really, unfortunately, in your own escapades with these boards, is that the boards are not consistent as far as how much abuse they can take. There are some boards that you could really kind of just like toss around, provide them like, I don't know, something crazy like 24 volts and they'll regulate it down. Other boards, especially like the off-the-shelf Uno ones, you don't want to do that. They're going to explode into a puff of smoke. Oh. Okay. Well, let's actually dig into the hardware portion. Oh. Let's actually dig into the hardware portion of the Arduinos. Let's take a look at what's actually on the board. Again, I'm not an EE, so this is gonna be kind of it's gonna be a little bit sketchy for me, but I do have some applicational experience with these. But regarding the power, the Arduino can provide power through or power output. You can power something from an Arduino, but you also need to power the Arduino. There are a couple ways to do that. The most common is from the USB port. That is a micro USB port up there. If you plug it into a computer, you will provide it power. In fact, let's do it right now. Oh, that's not a USB port. Arduino. If you plug the Arduino in to the USB, it'll provide it power. What kind of power is it providing? It is providing around 5 volts. I'm not sure how much amps it can go up to. I'm not sure how many amps it could go up to, but certainly enough for any sort of computational needs. Things get a little bit more complicated though, if you need it to be austere. If you don't want it connected to a computer, it gets a little bit more complicated. When you wire, when you wire the Arduino, if you want to power it from batteries, for instance, you need to connect it into the VCC and the ground pins. Any ground pin is fine, but power incoming needs to go to the VCC. This is very basic. If you have ever used an Arduino, probably already know this. But where this gets kind of unfunny is that if you're not really sure of how much power you're providing to the Arduino, you don't know the voltage. If you're just powering straight from a LiPo, bad things can happen. You can also power it from the raw. Not much, not a huge difference, but it is, I would say, from my own personal experience, power it from the VCC. And never from the GPIO pins. This could cause very bad things like instantaneous death of the microcontroller. That happens. It will happen to you if you ever use Arduino after this workshop. So these pins on the side are just based on whatever is provided from the microcontroller. As for why the microcontroller has multiple grounds, I can only guess as to say that it's for usability or utility reasons. It's nice to have grounds on both sides. And also if you're connecting everything to the same ground. So if you connect everything to the same ground on one pin, you can see how it might have some issues as far as flooding or other issues like that. Only guessing, not sure. Don't look it up. Okay, so Arduino's work with 5-volt TTL. Can anyone tell me what TTL means? TTL, okay. TTL is just 5 volts transistor to transistor logic. The transistors inside the microcontroller are working at 5 volts. I can't speak on anything more than that. I'm not an E. But what this also sort of implies is that in a electrical engineering standpoint, the microcontroller in terms of binary will interpret 5 volts as high or 1 and 0 volts as low or 0. So if you think of a single transistor, if it is enabled, if its value is 1, it has 5 volts across it. If it's 0, 0 volts across it, or the reverse actually thing. But another complicating factor is that other Arduino type boards like the ESP32, the Raspberry Pi, they use 3.3 volts TTL instead. This can cause problems if you're trying to power your Arduino, or if you're trying to power those boards with something that you would traditionally power a Arduino with. This comes more into play if you are designing your own PCBs, not necessarily if you're just slapping in an ESP instead of a Arduino. The pins might change. But usually an ESP32 or Raspberry Pi probably has a regulator in there, so it's not that big of a deal. By the way, just to break up the monotony, how many what's the major breakdown in here? How many are EEs? Couple of EEs. So wait, what are the rest of you guys? You're like MEs, CS? All right, that's pretty interesting. Okay, let me change up my approach. So let's talk about GPIO. So GPIO stands for General Purpose Input Output Pins. Anytime you need to have the microcontroller read or output any sort of signal, you use a GPIO pin. For the Arduino Pro Micro, which is what you will be using in the lab portion, all GPIO pins are digital pins. You could use them as digital pins. This implies that you can read and write from them, digital signals specifically. Some, but not all, are analog pins. In this specific pin out diagram, anything with this green sort of bubble that says A0, A1, A2, A3, those are pins that can be used as analog pins. These analog pins are specifically for analog reads, not necessarily analog writes. I've had a lot of heartbreak in interpreting analog pins as being able to output an analog signal. Not only is that kind of stupid if you're an EE and you have like any sort of experience with like manipulating analog signals, obviously you can't do that with a 32U4, but I tried. But as far as sort of trying to mimic an analog signal, because there are some situations where you need a variable voltage, you can do that using PWM. PWM is specifically a write operation that is done, I believe actually. Okay, yeah, so the Pro Micro, any of these check marked pins are PWM. On other microcontrollers, it gets kind of weird because all of them could be used as PWMs, but for this one specifically, only specific pins are enabled for PWM. Getting into some of the more communication-oriented pins, we have UR-SPI and I2C. I can't say much about using these. I've only used SPI a couple of times, but basically it is a bus or a way of communicating actually quite quickly with other microcontrollers. I2C, a little bit slower, UR a little bit slower. You know how it is. As far as what you'll be doing in the lab, there you won't have to worry about SPI, UR, I2C. Not that big of a deal, especially since we're not interacting with the radio module. If we were interacting with the radio module, then we would actually have to pay attention to that. But let's go ahead and get into some of the more electrical components of the Arduino. All right. All right, so there's a little bit of carryover information here from the previous Arduino workshop, but we'll go ahead and get into it. So anytime you have an analog signal that you need to convert to digital, how you would do this is you would measure the changing voltage signals. The real world example that is given here is used to read the potentiometer values from a joystick on the controller. We're not using controllers right now, but that is sort of an example of how you would want to read, for instance, an analog sensor like a potentiometer or any sort of older sensor, really, that you would want to read it in terms of a digital value that you could actually pull in the code. There is an implied importance of resolution here. Basically from 0 volts to 5 volts, which is what the microcontroller operates at, there's only a certain amount of discrete steps that it can split the 5 volts into in order to derive an integer value from. I believe for some it's like 0 to 1024. 0 being 0 volts, 1024 as in like an integer count of 1024 means 5 volts. This is basically how you interpret analog signals into a digital value. Note that there is somewhat of a correlation between being able to output PWM and being able to bring analog signals. Rather, these specifically, if I recall correctly, just a side note, not important. These pins specifically are able to output a PWM at a frequency that is increased above the rest of the PWM enabled pins. Just a idiosyncrasy, just a weird thing specific to this microcontroller. But let's actually talk about PWM. All right, so for my CEs and EEs, how many of you have talked about PWM? What about just anyone in general? Have like you guys heard the term PWM? Have you used PWM in any of your projects? A little bit, all right. So I'm gonna front load you with a application first instead of just telling you what it is. When you want to spin a motor at a specific speed, how would you do this? Well, how you would do this is take a look at how you actually put a motor in motion. You put a voltage across it. Let's say 0 to 7.2 volts is usually what motors are running at these days at this size. Well, the problem is that there's no actual easy way really to just modulate that. You could put a potentiometer, I guess, to drop the voltage. So say if you want to run the motor at half power, you would run 7.2 divided by 2. What is that? Okay, whatever half of 7.2, okay. Give me a break, I'm running a presentation. But you would run it at half the voltage in order to get like half the speed. The relationship between voltage and speed actually isn't that direct, but for all intents and purposes, if you need to drop the voltage in order to drop the speed, you need to do it in a way that the microcontroller is actually capable of. The microcontroller cannot directly manipulate analog voltage. So the way that we get around it is we try to approach like an average voltage. So what you can do is you could drop the voltage, you can create like a square wave almost in order to give an average voltage at a certain period of time. So say, so if we go back to the car then, actually, instead of giving it a direct like and smooth 3.5 volts, we'll just say 3.5 volts. What we would do is we'd actually send a square wave looking kind of signal that is not actually like a smooth, you look on it on an oscilloscope, it's not a smooth line, but rather it's kind of choppy, but the end effect is the same. The average voltage is 3.5, therefore the motor moves at a lower speed. That is how you control a motor. But let's go back to using it on an Arduino. PWM is used to write an output signal to an LED or a motor or any other kind of driver circuit. Arduinos cannot output a specific DC analog voltage value. We just covered that. And we can vary the pulse width of the signal at a high frequency to sort of trick the output, thinking it has a lower voltage. This is what I was sort of saying with the average voltage or averaging out the voltage. This example doesn't just apply to motors. You could use LEDs. In fact, that's how you sort of get an LED to dim. is if you put a PWM voltage across it instead of just analog, just full bore relay style, just full bore 5 volts, 0 volts. It turns out if you just flicker the voltage off and on at a certain interval, at a fast interval, it'll dim it. Pretty dang useful. That is what a PWM cycle looks like. PWMs, how we sort of subdivide them, or not subdivide, but how we say like 0 to 100% power in terms of PWM. We break it down into duty cycle. 0% duty cycle is like, imagine it's like 0 volts. 100% duty cycle is like 7.2 volts. 50% is half of 7.2 volts, stuff like that. It is split up into a square wave, as you can see. The goal is to just bring the average voltage down. So this is where the fun stops. Let's get into software. This is my specialty. So Arduino, how do we program them? How do we code them? So there's a lot of different ways. MicroPython, Arduino has its own IDE. In fact, I can just show you that right now. It's its own IDE. It's on light mode right now, which is not a great thing. But as you can see, you can go on here, just write some sort of code. And it's pretty lightweight, and you can just download straight to it. Not that big of a deal. MicroPython is a little bit newer, as far as I know. It is primarily used in, I'm not sure if any of you guys are like plugged into a Makersphere, but there is Raspberry Pi has their Arduino-like boards that traditionally are built to use MicroPython. I have no experience with MicroPython. If you want to use it for this lab, go ahead, knock yourself out. You can also code straight to it using C and C++. In fact, the Arduino sort of shell that the IDE interacts directly with is a weird fusion of C and C++. It incorporates some features of C++, but it retains some of the formatting, especially aspects of C. More complicated boards, like the ESP32, as previously mentioned, can be programmed with MicroPython. The other one is like, I forgot what the Raspberry Pi Associate is called, but you program it in MicroPython and you connect it, or the way you actually like flash the firmware to it is with USB serial. Arduino has a sort of high level functionality to work with the GPIO, meaning that your job is a lot easier. You don't have to be a CS major in order to understand how to directly interact with the libraries. You just type in one little command and that's it. You can also interact with the ADC as well as the PWMs. Not that big of a deal. So of you, how many of you have heard of things like RTOS, real-time operating systems, half-time operating systems-ish? All right. Well, the Arduino is not an RTOS. It is not that advanced. However, it does have a setup and a loop provided for you. If you've used Arduino, this is probably extremely familiar to you, but basically setup runs once and you put any of your initializations, your variable initializations that will be used later into here and the loop. And this loop just runs over and over again on the Arduino. And that's where you put a lot of your logic that needs to take place over time. Above this, basically above it, like physically above this, is where you should define all of your library installations, your variables, your pin locations, and your class setups. Let's take a look at that right now. Actually, so you can see that we have a wide variety of pin definitions. This is sort of a carryover, like we were talking about with C, is these define macros. Basically, we're just putting a number to like the pin, the GPIO pins, and we're just doing it for every single thing that we are using with the Arduino. Below that a little bit more is we have some variables that we'll be using later. Who here knows a programming language? What is long? Yeah, it's N32 or N64, I guess. It's depends on the compiler, unfortunately. Double is a floating point value, takes into account decimals. Integer is just your normal N16, N8. Small size integers. That's how it would be. Let's talk about setup again. So setup runs once. Setup runs once. Don't put anything that you need to have happen twice in setup because it only happens once. But if you need something to happen over and over again, as long as the Arduino is on, put it in the loop function. The loop function. This is where all your logic, all your reading, all your writing, this is where the actual meat of your code happens. This is the part where you put all of the fancy logic that you've come up with, all of the algorithms that you've come up with in order to, I don't know, do something. It's where you program, it's where you say motor, like go full power. It's where you say, read the ultrasonic sensor. It's where you say, read the IR sensor. That's where it needs to go. So this is a hashtag define is called a macro specifically for C. It names a constant value specifically to the script, such as a GPIO pin. It's a replacement for const, which means constant, which means it is defined in memory. It can't be changed. What's up?
You want to use the define to determine what the pins are.
I won't say it's the only thing you can use it for. You can use it if you have like, say you need to define pi up to a certain decimal point, you would use hashtag define pi, and then you would actually like type out pi to that link. It's anything that you need to be stored in memory that won't be changed later, but that you need to reference like more than once. It's sort of a tough thing to conceptualize because I don't know. It's like to me for a while, like variables were all the same to me, but this macro actually isn't a variable. It's a sort of thing that is stored in memory, a value that is stored in memory that you can reference over and over. There are other ways to do this. This is a very old-fashioned way. A lot of people still do this. I still do this. Is you just put const int LED pin. It's pretty much the same thing. There are some compiler benefits to doing any other way. Like, for example, I could just say like const int my int is equal to 8. That will store the value of 8 in memory, and I can't change it, but it's very fast to reference it. Ooh. There is a key syntax to it. If you've used any sort of programming language, it's not at all complex to you. You just do hashtag define, you name the variable, and you give the variable a value. No big deal. There's an example. If you're going to do this later, it is done for you in the skeleton code, but you still should still look at it, understand it, see what's happening. That is what it looks like in the skeleton code, but this specifically for a controller that doesn't exist anymore. Yeah, you're just defining the GPIO pins on the Arduino that are being populated. One little thing that is a little confusing is that you could actually reference pins on the Arduino. It'll say A6 or A1 on the Arduino. You can directly reference it. You don't have to look up the actual value of A6 on the pinout. You could just say A6. This is a feature that is inherent to the Arduino ecosystem. If you're using the Arduino IDE, the Arduino library, it's a namespace that is kind of useful if you're prototyping rapidly. And there's the, this is how you define pins. The actual pin numbers are emitted right here. We used to make you fill them out. You don't have to do that right now. There is a way, so say you plugged in a sensor to your Arduino. Well, how do you read that sensor? How do you initialize that sensor? Well, you use the pin mode command or function. Whenever you have an input or an output, you need to initialize it. Pin mode will set the pin mode on the Arduino to input or output. It is a C style function. So it has two parameters. It has the pin name, which you define using the hashtag define or constant, and it has the pin state. Pin state can be input, output, input pull up, if you need a pull up resistor, or input pull down too. These are two examples of if a pin is an output or if a pin is an input. Inputs, for all intents and purposes, are for inputting sensor data. If you need to read a sensor, its data pin should be set to input. If you need to sort of drive an LED, if you need to drive PWM to somewhere, that pin should be sent as an output. You'll run into problems if you don't initialize your pins correctly. This is a key part of the workflow that needs to be followed every single time you do a project with an Arduino. There is no getting around it. There is no reason that you should go around it. You should do it every single time. Here's what it looks like in the skeleton code that you're about to use later. How are we doing on time? All right, cool. These are already done for you this time. It'll be referenced. Just make sure you know. Anyone know what a pull-up resistor is? I'm happy to see some guesses. Don't worry. I didn't know until like last semester. But basically it's just a helper resistor that sort of differentiates 0 from 5 volts on to off on a pin. If it's just floating, like if it has no connection to ground, if it has no reference voltage, then you'll get some sort of like weird noises, weird interference. And if like someone like takes a taser and goes next to it, then the pin like could like spontaneously go off. Not that huge of a deal, but it is. There's no reason why you shouldn't take advantage of an input pull-up as far as certain digital reads go. Oh yeah, there's a diagram of a pull-up resistor if you were looking for sort of a circuit diagram example of what that means. Just go. All right, so your digital reads and writes are the bread and butter of Arduinos. It's how you interact with pins as far as digital signals go. A digital write is used to write a high or a low value, a binary high or a low value, 5 volts, 0 volts, 5 volts high, 0 volts low. Please remember that. To a pin, and it is used for any sort of output. If you need to drive an LED, if you need to drive a motor, anything. Digital output, digital write, right to the pin. On the other hand, you have your digital reads, and all it needs is its pin name, and it'll read the value at that pin. Specifically, it'll read a high, 5 volts, or a low, 0 volts. It'll store that into a variable for future use. So let's go ahead. What does that look like in code? Well, that looks like this. Actually, we'll go to loop. Look at that. We'll say so IR1 data is equal to digital read IR1 what the IR1. So, that's center screen. Right. IR1 data, which is just an integer variable, is equal to the digital read of the IR1 pin. That is how you transmit data from the physical pin into your code structures. It's how you sort of store that kind of data. Note that in digital write, you actually have to provide it a sort of status. So if you need that pin to go high, you say digital write pin high or low. You literally type out low or high. Or you could do 0 or 1. So this is where it gets a little bit even more in the weeds, because as far as analog writes, it's a little bit weird. But in sort of the same way, remember how, 1024, that number is kind of familiar. It's because that's how the Arduino splits up 0 to 5 volts. So if you need to provide a pin, not 5 volts, not 0 volts, but like 4.5 or something, you would find the associate value of 0 to 1024 that corresponds to 4.5 volts. Be aware though, this is not an analog value. This is a PWM value. That's how you regulate the speed of RC car motors, and you use it. You can also like set it straight, like high, like digital. But if you need to modulate it, you can give it a different value. Analog reads though, pretty much the same sort of idea as a digital read, bearing in mind that it can only happen on specific pins. And it will spit you out a range of values from 0 to 1024. This is an example of how to analog read. Not that big of a deal. That 13 is the pin. You can also see on this figure right here, you have what the PWM looks like at different command parameters. For instance, if you do analog write at 127, it'll give you this sort of 50% duty cycle. So whatever the reference voltage is, say 5 volts, it'll give you half of that at 127. Note that it's not like a percentage, it's 0 to 1024, a little bit stranger. Like 191 is 75%, 64 is 25%. Fun stuff. So why is it 0 to 1024? Well, that's the analog resolution. Check the data sheets. Check the data sheets. Check the data sheets. Every single time you use an Arduino, check the data sheets. Why? Because it'll tell you exactly what will happen if you do an analog read, you do an analog write. If you're getting like strange erroneous values from reading analog signals, probably a reason. It's probably because the ADC on the board is different than what you're used to. The resolution of the Arduino that we are using has these specs: 10 bits, 0 to 1023, with the resolution of PWM at 8 bits, 0 to 255. Very common. These are very common values, and you'll see them all the time, but sometimes they'll be different. The higher the resolution, more sensitive control system you will have. So this has an implication. If you need a very sensitive control system, say you're doing like an inverted pendulum where you need to balance a weight with one motor, you need a more sensitive ADC. You need more resolution. There are other ways that you can get around here. Who's an ME again? Sorry. Or MEs. If you have like an analog potentiometer, what you could do is you could gear down the shaft, and that'll give you more resolution with the same amount of ticks. Ticks being 0 to 1023 or 0 to 255. It'll give you more ticks, and that'll give you a more sensitive system. But that's not always a good thing. You don't always want to introduce a gear train to your designs. You don't always want to do that. So you should get a more sensitive or a higher analog resolution microcontroller. Don't worry about that warning. Okay, so there's a really cool function in the Arduino shell that is called map. Map is how you it'll automatically, if you give it a range of values, it'll automatically map that range of values to a different range of values. Well, what do I mean by that? You transfer a number, say if you have like 0 to 100, you could transfer 50 in that 0 to 100 to whatever half of 0 to 1024 is. Might be able to already see what the implication for that is. You do lose out on resolution due to hardware constraints doing that though. What are some applications of using the map? Well, you can sort of, we'll ignore this. If you notice that the ADC on the Arduino is 10-bit, while the PWM is 8-bit. Well, you need a way to sort of map either the PWM to the ADC to the PWM. You do that using the map function. It's sort of annoying because of how many parameters it has, but basically if you have a value between two old ranges of numbers, or two old numbers, if it's between those two, it'll map it to whatever the new range is. Look at this. We have a potentiometer value. Notice that this is a variable. It can change due to time. It doesn't necessarily have to be a constant. It can be changed. That value is known to be 0 to 1023. But we want it to be 0 to 255 because we want to directly use that value in order to say power pivot PWM in.
So that's just like a linear distribution then?
Yeah, pretty much. There's a little bit of like weird fast math going on behind the scenes, but we don't have to get into it. You do lose resolution. It'll be like sticky between new values because of the way that it does it. Okay, so working backwards, we have the include macro. Whenever you use an Arduino, you should always be using libraries because people have done like pretty much all the work for you. You just need a plug and play. There's no reason for you to like reinvent the wheel every time you start a new project. So what that means is you have to include libraries. Most sensors already have a sort of library already built for them. So you don't have to like directly interact with pins necessarily, or directly do any sort of EE, some nitty-gritty logic that doesn't really make sense in the scope of any sort of project you're doing. An example is the wire library, which allows you to communicate using I2C. You don't have to do like interrupt service routines with I2C in order to use it in Arduinos. Just use the damn library. This is how you do it. It's that simple. And you already have, each library will typically have like documentation associated with it. In fact, let's look Arduino wire library. Boom, we have functions that we could use. So what does this look like in code though? Well, let's open our IDE. Let's include wire.h. We can now, if we want to, just okay, wait, hold on. Yeah, okay, so we could now just reference wire directly. Something like that. We can give it a specific address. Typically, I just do zeros. Not necessary, but that's pretty much how you use a library. Not that big of a deal. Not even that hard. As far as this lab goes, you do have some required libraries. Well, actually, no, you don't. You don't have to use any libraries for this one. But if you're using the radio module, for instance, it is already equipped on this on the cards that you're getting. There's a radio module on it. feel free to use it for some reason. You can just cause, I guess, RF interference and just annoy the IT people. I totally support it. But yeah, if you want to do that, you'd have to use the NRF libraries, which actually, like all of these, are just to use the radio module. That's sort of the drawback of using a bunch of libraries, is you end up having a lot of dependencies. As far as using libraries in the Arduino ecosystem, you just kind of go over here. It has its own built-in tool, so you can search for, like, if boom, ultrasonic. Yep. We have like any sort of, you can just straight up download like libraries and just use them. Oh, let's do that. All right, let's get into some cool stuff. So we'll see specific, I'm not sure. Data structures, yay. So this is the worst part of software engineering, in my opinion, is data structures, but C has its own built-in sort of methodology of doing data structures. A data structure is very broadly a collection of different types of variables. Obviously, you have your ints, you have your floats, you have your longs, doubles, strings, character strings, C strings, whatever. It could even be like any sort of object too. You can create your own kind of variable types that you can also include into a single data structure. It is somewhat similar to an array, but it has its own sort of benefits. For instance, you can reference directly any one of these values directly by name. You don't have to, I don't know, look for the index in an array. It's nice because you can directly interact with data structures. You can send data structures, you can receive data structures, and it all comes packaged with, or it packages all of the values that are inherited or inherent to that data structure. So right here, you can see, okay, well, let's work through this. You have the struct data structure. Struct is like a very basic C-based data structure. It has all of these values packaged up inside of it. The sort of weird thing is that you have to not only reference the structure of the data structure, but you also have to create a data structure. That's what this is. If you notice like how like, oh, light and then write SW, how that's referencing or creating a byte variable, you need to create a structure. So we have CMD packet, which is the type CMD packet, and we're just giving it a name. That is how you instantiate a data structure, not just create it. Then you can just assign values and set any of the child values. You'll see right here we have digital read that you can just set. Commonly, you'll package all of your sensors together into a single data structure, and you'll just deposit all of the data like this. It makes it easier to like send stuff over radio too, because you can just format it as a packet and then just send the data structure as a packet, and you can read it. Moving more into the hardware side, all right, let's speed through it. You guys know what an LED is. There's 0% chance that you don't know what an LED is. Please tell me you guys know what an LED is. It's a light. It's a light. You send current through it and it lights up. It has an anode and a cathode, and you commonly use these to just blow them up because you forgot a resistor or something. That is their primary use case. Their secondary use case is that they provide colored light. LEDs are like almost, it's like it's like a USB port, like it's almost always backwards. You almost always blow one up because of it, every single time. Motors, the most exciting invention of the 1800s. We have electric motors. They spin when you pass voltage through. We could get into like the anatomy of an electric motor. It literally does not matter though. You just want to pass voltage through it. If you actually are interested in that sort of thing, there's like you take a whole class on it if you want to. It passes current through a coil wire, which generates a magnetic field, which turns the shaft. It's not necessarily polar. You can connect the terminals backwards and it'll just rotate the opposite direction as if it was just normal. This has implications, and if you want to go reverse as well as turn, usually motor controllers will handle that sort of polarity for you. Hey, look, a motor controller. This is the old but most popular motor controller on the market for makers. I absolutely hate it. It can change motor directions based on two digital inputs. It gets a little bit more complicated than that, unfortunately, just because how old it is. The pinout is so annoying that we've taken care of it for you in the skeleton code. Look at this table just to control like the polarity of motors. Wow, that sucks. But the overall architecture of it is roughly the same. You can't power a motor from the Arduino. Not only will it not provide enough power, but it'll probably explode your Arduino. So it needs its own external power connected to batteries or connected to the power source or whatever. It needs to provide that to the motor controller so it can feed the motor the correct amount of power. This is an OLED screen. We're not going to directly interact with these in this lab. However, it's here. You can use OLED screens. It's not like an OLED monitor, but you can like draw shapes with an Arduino using this module. It has its own library. Use the library. You can, draw shapes, draw text. You could print on it. All that sort of fun stuff. Okay, so this is what I was hired to do. Not for this lab or not for this workshop, but for my actual job. Control theory is the study of how a system responds to stimulus. I know that sounds like completely arbitrary and like a little bit like what does that even mean? But let's work through it. What does it take to make an unstable system stable? If the most common reference is like a pendulum. How do you stabilize a pendulum? Well, you can induce a sort of like opposing motion in order to deaden the pendulum. You can move your finger in order to like oppose the movement of the pendulum. That is a mechanical example of an implementation of control theory. Practically, there are two sort of main methods of introducing control into a unstable system or uncontrolled system. PID, which is this horrendous looking thing. Nobody has taken like control theory, right? So I can just be wrong. Okay, that's great. This is what the math implementation of a PID looks like. Basically, if you want to like, say you had a gyroscope on this robot and you want it to point it to a specific angle, you can provide angle and it'll output a correcting value to the motors that will specifically like allow it to orient straight to that gyroscope angle very accurately. Less accurately is if you want to use bang bang. Bang bang is just the P portion of PID, but that's industry secret, I guess. It's just if you were to say like, okay, if the gyroscope angle is currently 32, but it needs to be 64, the bang bang value is just the difference between them. And you give that bang bang value to, I don't know, the motor, and then it will turn, it'll like overshoot rock a lot, and it might even just like completely overshoot. But that's genuinely the most simple control algorithm that is out there. It is used in your HVAC system. Guarantee it. Modern control theory is tackled in software. It is tackled in code almost strictly these days with the advent of microcontrollers. It used to be actually like pneumatic or hydraulic control systems that would steer ships and stuff like that. Those things are beasts. They're like room-sized, like pneumatic computers. It's actually insane. This is an extremely in-demand proficiency in software engineering. I can only assign myself with that and the recruiters that I've talked to. But if you have any sort of interest in programming robotics, this is where you start your journey. This is the first thing you should learn in terms of if you want to actually program those robotic arms, if you want to actually work for Tesla and do autonomous driving, pay attention to your controls class. But what does this mean for us? Well, we're going to be doing a line following robot. It is robotic autonomous driving at its simplest. How do we get a robot to follow a line? We need a couple of sensors. We need infrared detector emitter pairs. We can use an ultrasonic sensor, and we need obviously motors to drive the wheels. A bang-bang controller is the least complex way to create a stable line follower. Well, what does bang-bang mean in this context? Well, you see this diagram, we see these two orange like circles. These are 2 orange circles. Those are your IR sensors, your line sensors. If one ball sees the line, see if these, like if this right circle sees the line, then that implies that the robot needs to rotate this way in order to stay on the line. So you would program that kind of logic into your Arduino, where if right IR sensor sees line, turn right. If left IR sensor sees line, turn left. In the end, you get a sort of robot that'll follow the line. It'll look janky, but it'll follow the line. And you can even optimize it to a point where it smoothly follows the line. You don't have to, but it is possible. But let's look at these sensors actually in focus. The infrared emitter detector is this entire unit. You don't have to worry about 4 different sensors for emitting and detecting. It's all in one package. It will provide you a binary, an on or an off input, meaning that if the IR sensor, which is right here, is probably insanely hard for you to see. If it sees a white background, it'll be off. If it sees a dark background, it'll be on. Using that, you can sort of say you can know basically if the robot's on the line or if it's not. I might have had the values backwards actually. Sorry. Notably, there's a potentiometer right here. It's that blue box. These require calibration. And honestly, it is probably the hardest thing that you will tackle in this lab. Is just calibrating it so it gets just right. You need to get in there with like a screwdriver. It's a whole thing. The ultrasonic rangefinder is also aboard here. It provides ranging data. Actually, these are all right. It'll provide you like range. It's not it doesn't naturally spit out like millimeters or inches. It'll give you like this weird like arbitrary number that you have to then form math on in order to get useful data. But you could use it to detect an obstruction in front of a bot before it actually hits. If in Teslas and these new sort of vehicles that have autonomous, they actually use radar, but they use much of the same logic in order to get the same sort of data. Well, how do we use all of this? How do we like synthesize all of these sensors into a workable code architecture? Well, we already mentioned this, is if the right IR sensor sees the black line, turn right. If the left IR sensor sees the black line, turn left. If none of them see the black line, just go forward. It's that simple. That is bang bang control. Welcome to control theory. Ultrasonic collision detection is its own separate approach. If the ultrasonic rangefinder value falls below a certain threshold, stop. That is how you avoid detection. It is that simple. Here is the code. Here is some like code snippets that you will be directly using. Notice that I have included the pin mode declarations for each pin. I don't know how. Yeah, initialization. I'm pretty sure this is already done. But in terms of reading the actual data from the IR sensor, this is what it looks like. You're just depositing IR data into a variable, or you're depositing the data into a data variable from the pin. This is a very easy way to get that kind of behavior, to get that kind of, if the right IR sensor doesn't see the line, but the left IR sensor doesn't see the line, go forward. That's simple. There's no need to go ham on this programming. You can get complex behavior just by using if statements. Now it's not great, but it'll get you there. This is how you use the range. If you use the get distance function and it falls below 15, stop. It is that simple. There's no need to overcomplicate this, but man, you will be still spending a lot of time calibrating that. Go ahead.
Are these functions like from libraries or do we have to predefine them?
Some of them should be for already. I believe this is the skeleton code that you guys will be using. We already have written forward for you. It looks like like this is like chunky code, but it's doing parts of these motor controllers, man. I'm telling you, they're the devil. Yeah, like look at this. It's already written for you, so you can mix and match. You don't have to use all of them, but you can get some pretty smooth behavior by using all of them. There are better ways to do it, for sure. But for the time you have allotted, should be good enough. Yeah, it's 5:27 right now.
Wait, I thought we moved like 6.
That was last time, but apparently this time.
Can you message Yash to see what they're up to right now? All right, so who here has a computer? Can you guys go to this link?
Mind putting that full screen?
Oh yeah, sorry. Yeah, you should download the Arduino IDE, the new one. The Arduino IDE 2.0. Actually, let's go there right now. Yeah, there's a Mac. Huh?
Good.
That was good.
I have so many photos for your LinkedIn.
Oh,
That's
let's
crazy.
go.
Your LinkedIn as well looks so nice. Yeah, guys, I'm putting it in the Hyperloop general right now. Wait, so we're moving at 5:30?
We'll move when everyone's squared away with the IDE. It's one of the BSC rooms. What? It's pretty good. I was like, I don't know. I had to add like the control theory stuff, but pretty much the other stuff is recycled.
I have like the.
Does everyone have their teams? Are we getting into their time?
We'll figure something out.
Because if a team doesn't have a laptop,
Not too much difference, just being in the camera.
How many bots do we have?
10?
No, we have more than 10.
Well, I think we set up like 11.
Oh, yeah.
Is everyone just downloading?
I tried typing that in. Down like that.
Oh, no, wait, this is not public.
Send a code snippet.
Oh, no.
Score. Let's check it out here.
Yeah, wait. What? There's no way.
Is it not public?
I don't know. It should be.
You better be the first 20 lush I see. Okay. Can we stop recording?
Chris, are you still here?
Do a cool outro. I want you to do a cool outro.
What? Should I play the YouTuber outro music?
That's my presentation.
See you guys next time.
I'm just telling him we're done.
We're sorting out software stuff.
He said, do a cool outro because it'll be in the front page of your LinkedIn.
Oh shit. How we doing? We having trouble?
I don't-
The Arduino